Let's look at a typical band diagram of such double junction, or also referred to as a tandem cell. On the left, the electronic band diagram of the amorphous silicon top cell is shown, and on the right, the electronic band diagram of nanocrystalline silicon bottom cell is shown. The bluish and green light is absorbed in the top cell and excite the mobile electrons and holes. The reddish light is absorbed in the bottom cell, exciting the charge carriers. Let's consider the two electron-hole pairs excited in the top and bottom cell. The hole generated in the amorphous top cell moves to the p layer. The electron excited in the bottom cell drifts to the n layer. Both can be collected at the front and back contacts. The electron excited in the top cell drifts to the n layer, and the holes generated in the nanocrystalline bottom cell drifts to the p layer. Similar like in the 3,5 multijunction, the electrons and holes have to recombine at the recombination tunnel junction between the n layer of the top cell and the p layer of the bottom cell. Often, a very thin and defect-rich layer acts like a tunnel recombination junction here. Here, these electrons and holes recombine. Again, the total current density is equal to that of the junction with the lowest current density. It means that in an optimized multi-junction cell, all current densities in the various subcells have to be matched to achieve the best spectral utilization. Let's look to the JV curves of a single junction amorphous silicon solar cell and that of a single junction nanocrystalline silicon solar cell. The high bandgap amorphous silicon has a high open circuit voltage of, let's say, 0.9 volts and a relatively low short circuit current density of 50 milliamps per square centimeters. Whereas the low bandgap material of nanocrystalline silicon has a lower open circuit voltage of 0.5 volts and a higher short circuit current density of 25 milliamps per square centimeters. How would the JV curve of the corresponding tandem cell look like? If you would make a multi-junction of both components, we would get a cell with an open circuit voltage equal to the sum of the open circuit voltages of the individual single cells. The resulting current density of the double junction is lower than the currents in both bottom cells. The total current utilization of the tandem cell is determined by the bottom cell, which is 25 milliamps per square centimeters. Given the examples of the single junction here, the best current matching of both cells would deliver 12.5 milliamps per square centimeters. Here you see an example of thin film silicon-based triple junction with an amorphous silicon top cell, an amorphous silicon germanium middle cell and a nanocrystalline silicon bottom cell, as developed at United Solar. The colored part in the spectral power density function represents the utilization of the solar spectrum by the individual cells. Blue represents the top cell, green represents the middle cell, and red represents the bottom cell. In this figure you see the EQE of the 3 PIN junctions of a record triple junction of United Solar. As you can see, the individual cells have various overlaps. They don't look like the block functions as we have seen for the 3.5 technologies. The light with the wavelengths below 450 nanometers are utilized by the top cell only. Wavelengths at 550 nanometers are utilized by the top cell and middle cell. Wavelengths at 650 nanometers are utilized by all three junctions. Wavelengths above 900 nanometers are only utilized by the bottom cell. Consequently, optimizing thin film silicon multi-junction solar cells is a complex interplay between the various thicknesses and light trapping concept used in the solar cell. In this slide you see the most studied and developed thin film silicon concept on lab scale. The record single junction amorphous silicon solar cell developed by Oerlikon Solar has an efficiency of 10.1%. The best single junction nanocrystalline silicon solar cell is 10.7%, as obtained by EPFL in Neuchâtel in Switzerland. The best result for a micromorph double junction or an amorphous nanocrystalline double junction is 12.3% obtained by Oerlikon Solar. LG in Korea has the record for the amorphous nanocrystalline triple junction with 13.4%. United Solar achieved an initial efficiency of 16.3% for the triple junction based on amorphous silicon germanium, and nanocrystalline silicon. However, the stability of the amorphous alloy used in this triple junction is a big issue. The hydrogenated amorphous silicon alloys suffer from light-induced degradation, and the stable efficiency drops below that of 13.4% as achieved by the amorphous nano-nano triple junction. The light-induced degradation, also referred to as the stable-Wronski effect, is one of the biggest challenges for the thin film solar cells. The recombination of light-excited charge carriers generate some metastable defects in the absorber layers. More bulk defects means enhanced charge carrier recombination in the bulk, which mainly affects the performance of the amorphous solar cells. The performance of amorphous solar cells relatively decrease with 10 to 15% due to light-induced degradation. And therefore, people talk about stabilized efficiency. If the stable-Wronski effect could be tackled, thin film silicon devices could achieve efficiencies well above 16%. Another aspect of thin film silicon solar cell is the current matching between the various solar cells. Textured surfaces are being used to scatter light into the various junctions to enhance the absorption path length, which allows to use thinner absorber layers. This becomes more important for the bottom cell, as this nanocrystalline silicon film is the thickest layer in the device and it has to absorb the most reddish part of the spectrum. Secondly, intermediate reflector layers are being used as a tool to manage the light management between the cells, like indicated by the blue layers. The top junction and bottom junctions are separated with a low reflective index material. Due to the large refractive index mismatch between this intermediate reflective layer and the top cell, more light is reflected back into the top cell. This allows the amorphous top cell to be made thinner and makes the device less sensitive to light-induced degradation. Nowadays, doped nanocrystalline silicon oxide layers are used as intermediate reflective layers. They have the bifunctionality of generating the built-in field over the absorber layers and to act as transparent intermediate reflective layers.
Let's go to the DMIS lab at the Delft University of Technology. We will show how thin film silicon solar cells are made on lab scale. Before deposition, the samples have to be cleaned in a so-called ultrasonic cleaning bath. The potential dirt and dust particles are removed. Since the solar cell device is only several hundreds of nanometers up to a few microns thick, a dust particle on the substrate will generate a shunt between the front and back contact in the final solar cell. Here we use a substrate that is coming from the Japanese Asahi Glass company and already has a TCO coating on it. The TCO coating is a fluorine doped tin oxide and is responsible for the hazy color. In this movie, we deposit a thin zinc oxide layer on top of the Asahi substrate to protect the tin oxide from the next processing steps. The substrate is mounted on a sample holder and put into a low lock. A low lock is a chamber in which the substrate is brought under low pressure before it's moved into the processing chamber. This avoids the processing chamber to be contaminated with various unwelcome atoms and molecules present in ambient air. During sputtering, the zinc oxide target is bombarded using an ionized noble gas like argon. The generated aluminum zinc oxide species are sputtered into the chamber and deposited onto the substrate. Here you see the sputtering plasma. After the sputtering processing step, we have a glass plate with a tin oxide with on top a very thin zinc oxide layer. Next, the samples are mounted into a different substrate holder. This substrate holder is used during the plasma-enhanced chemical vapor deposition step to deposit the various thin silicon films. Again, we use a load lock. The load lock allows access to the various chambers. Every chamber is dedicated to deposit a type of silicon layer: P-type silicon carbide, intrinsic amorphous or nanocrystalline silicon and n-doped amorphous silicon or n-doped nanocrystalline silicon. Typical precursor gases in the deposition plasmas are silane diluted with hydrogen. An RF bias between electrode plates generates a plasma. The silane is dissociated and the silicon containing radicals and ions are deposited on a substrate. Adding diborane or phosphine to the plasma makes the films p-type or n-type. Increasing the hydrogen content makes the films nanocrystalline instead of amorphous. The samples are moved from chamber to chamber through the load lock. After the various silicon deposition steps, the sample with a thin film silicon PIN junction on top looks like this. Next, the samples are covered by a mask. The mask determines the areas on the sample where the metal contacts are deposited. The samples are mounted into a processing chamber. Silver is used as source material and particles of silver are put in a boat. The silver is evaporated using an electron beam. The silver vapor deposits on the samples and form the back metal contacts. After taking the solar cell out of the E-beam evaporation setup, we can see the final silicon solar cell on lab scale. Every metal contact represents a solar cell.
The configuration of solar modules of thin film PV technologies are different from those based on crystalline silicon-based wafers. Here we will show the concept of how the solar cell in a thin film PV technology are processed and interconnected. We will show it here for a thin film silicon PV technology. In the next blocks we will discuss other thin film technologies like CIGS and cadmium telluride. Similar interconnection schemes are being used for these technologies. The solar module and its interconnection is processed in one process sequence. The substrate carrier of the module is a large glass substrate. On the glass plates the front TCO is deposited. Using intense lasers, lines of TCO are removed. This process is called laser scribing and determines the area of the solar cells. On top of the TCO, the various silicon layers are deposited, making the PV active part. After the silicon process step, a second laser scribing step is made. The metal back contact is deposited, after which the last laser scribe step is used. The whole cell is finished by covering it with an encapsulant material. In this interconnection scheme, the metal back contact is connected with the front zinc oxide contact of the next cell. A module consists out of long strips of solar cells which are interconnected. Here you see a picture of a micromorph tandem module. You can see the various solar cells and the laser scribes. The open circuit voltage of the module is determined by the number of solar cell strips that are connected in series. Note that shading effects on this type of module is different from that of wafer-based crystalline silicon solar cells. The best module efficiencies are in the order of 11% as achieved by companies like Tokyo Electron, Panasonic and Kaneka. Another advantage of thin film PV technology is that you have an option to deposit it on flexible substrates. Here I give an example of the Hyatt Solar company, who develops a technology that is deposited on a temporary aluminum foil. The entire solar cell is processed on the foil and encapsulated at the backside. Then the temporary substrate is etched away and the front side is encapsulated. This results in a very low weight flexible substrate which can be integrated in curved rooftop elements. The advantage of lightweight is that a professor can lift it quite easily. This technology can be installed on simple rooftop constructions that have a low maximum for the ballast weight. Compare this to glass-based solar panels. These can be quite heavy. Secondly, if the product is integrated into roof elements, it saves significantly on the installation cost, which has to become the largest contributor to the non-modular cost of a PV system. At the moment, only thin film silicon technologies have demonstrated flexible modules with reasonable efficiencies on lab scale. This was the quick introduction into thin film silicon PV technology. In view of time limitation, I did not talk about the thin film silicon junction crystalline solar cells. These are based on thermal crystallization of amorphous silicon deposited on non-wafer based substrates. On lab scale, close to 12% conversion efficiencies have been achieved with this approach as well. In the next block, I will talk about CIGS PV technology. This is the thin film PV technology which has the highest achieved efficiencies on both lab scale and module level. See you in the next block.